So welcome everyone to this Methods Hub seminar. And it gives me great pleasure to introduce Dr. Xiang Zhou for this seminar. Dr. Zhou is an associate professor in the Department of Sociology at Harvard University. And before he came to Harvard, he was a postdoc at Princeton, and he received his PhD in sociology and statistics from the University of Michigan. He's a faculty affiliate at many institutes, the Weatherhead Center for International Affairs, the Harvard Institute for Quantitative Social Science, the Harvard Center for Population Development Studies, and the Fairbanks Center for Chinese Studies. His research is really very innovative, and he's one of the very few people who develop new methods and approaches in the social sciences, such as for estimating inequality in the social sciences, and also paying particular attention to causal inference. And this is reflected in the very high quality of his research, which has appeared in the top sociological and statistical journals, including the American Sociological Review, the American Journal of Sociology, Journal of Political Economy, Journal of Royal Statistical Society, many more top scientific, statistical, and sociological journals. So the title of his talk today is Disparity Analysis, A Tale of Two Approaches. And he will speak for around 45 to 50 minutes. If you do have any questions, burning questions, please do put them in the chat. I can interrupt him if there are clarification questions. Otherwise, please do stay on for the Q&A after his talk. So Professor Zhou, please start whenever you're ready.
Okay, let me share my screen first. Okay, can everyone see my screen?
Yep, yes.
Excellent. So thank you very much, Terani, for having me here and for the very kind introduction. It's my great pleasure and honor to be presenting at Hong Kong U Sociology. So today I'm going to talk about my very new work on disparity analysis with my two students, Alexey Opasik and Lai Wei. Alexey Opasik is a third-year graduate student at Harvard, and Lai Wei is a fourth or fifth-year graduate student at Princeton. And because this is my first time presenting this work, it can be rough and maybe confusing at many places. So if you have any clarification questions during the talk, please feel free to interrupt, raise your hand, or just put your question in the chat box. Okay, first of all, let me give you a brief discussion of the history of what we call disparity analysis. We all know that social and economic inequalities are a perennial topic of sociological research. And to study patterns and trends of various forms of inequality, quantitative social science research has typically relied on statistical models linking the conditional mean or the conditional variance of an outcome of interest to a range of explanatory factors. And such models can be very useful for us to link the macro and micro to see how aggregate levels of inequality are shaped by the distribution and also the effects of individual level factors. And I have been a practitioner of this approach myself since my graduate school. And here, let me share with you one of my early papers on the roles of increasing returns to education, educational expansion, and also privatization in the rise of earnings inequality in urban China. So to link the macro level inequality to individual level and structural changes, I used a technique called the variance function regression, which models both the mean and also the variance of earnings as a function of explanatory variables, such as education and the sector of employment. While this technique is useful for analyzing the overall degree of inequality, sociologists are typically more interested in disparities between groups, or what Charles Tilly calls categorical inequality. So to study categorical inequality, a widely used technique is the Kitagawa-Blinder-Ohaka method, where the goal is to decompose differences in the mean outcome of two groups into various explanatory factors. Specifically, we fit two linear models separately for advantage group and for disadvantage group, say men and women. Then we use these models to decompose the between group disparity, such as the gender wage gap, into two parts. A part explained by group differences in background characteristics, say education and work experience, and an unexplained part, often called residual inequality, which is often associated with labor market discrimination. And for a long time, this method was, and still is by many sociologists, called the Blinder-Oaxaca method, because they were independently proposed by economists Blinder and Oaxaca in 1973. However, in recent years, it has been recognized that pretty much the same decomposition was proposed in 1955, 18 years earlier by sociologist Evelyn Kitagawa, a sociologist based in Chicago, who was also a PA president. So this is why we now call the method the Kitagawa Blinder-Oaxaca method, or the KBO decomposition. So the KBO method is often used to study disparities across categories of gender, race, or class. Specifically, we can use it to answer questions like, to what extent can the gender wage gap be explained by gender differences in education and work experience, or to what extent can the black-white income gap be explained by black-white differences in class origin? So the canonical KBO method decomposes the gap in mean outcomes based on linear models. But various extensions of the KBO method have been proposed, which include decomposition based on nonlinear outcome models, such as low-bit and poor-bit models, decomposition based on models for group membership. So instead of fitting outcome models, we could also fit models for group membership and do the same decomposition. And decomposition of differences in distributional characteristics, such as quantiles and variance. And the KBO method is useful for quantifying contributions of various factors to a disparity of interest. But it does so in a counting or descriptive sense, which means it has no causal interpretations. For example, we could use it to assess the extent to which the black-white gap in college completion rates in the US can be explained by their differences in college quality, as Black students are less likely to attend higher quality colleges compared with white students. But such a decomposition makes no causal claims about either the effect of race or effect of college quality. First, let me elaborate on this point a little bit. First, we know that it can be philosophically flawed to talk about the causal effects of gender or race or other characteristics that are seemingly immutable, right? And most practitioners of the KBO method are deeply aware of this. But a more subtle and more important point is that the KBO method also doesn't speak to the causal effects of the explanatory variable unless potential confounders of their relationship with the outcome are adjusted for. But this is often not the case. So since the KBO method itself don't have explicit causal interpretations, they are not well suited for answering policy-related questions. So what can we do? Should we just be content with purely descriptive results and abstain from making, policy recommendations, or should we make bold but perhaps irresponsible policy recommendations? We can see that neither is very satisfactory. But the KBO decomposition itself is not tailored to answer policy relevant questions. And from a policy standpoint, we would be more interested in questions like, what would be the black-white gap in completion rates if college quality was equalized between Black and white college goers, or equalized, conditional on some metric of merit, such as test scores on high school GPA. But such questions are not targeted by the decomposition itself. Okay. So to address such questions, there's an emerging literature in both sociology and in epidemiology that incorporates the language and the logic of causal inference into the study of categorical inequality, or what we call disparities. And here are a few notable studies. First, Jackson and Vanderwell in 2018, in an epidemiology paper, they consider racial disparities in wages and other outcomes under hypothetical interventions that equalize childhood SES, test score, or both. So in that paper, they use test score as a proxy of educational attainment. Then in the following year, I had an ASR paper where I consider levels of intergenerational income mobility under also a hypothetical intervention that sets everyone's educational level to bachelor's degree, and to see how intergenerational income mobility would change in such a hypothetical scenario. And inspired by these papers, Ian Lundberg, a graduate student at Princeton, who is now an assistant professor at Cornell, proposed the concept of gap closing estimands and introduced a range of estimators such as regression imputation, weighting, and doubly robust methods for estimation. And more recently, with the student Guanghui Pan, now at Oxford, I wrote a paper on higher education and the black-white earnings gap, where we used extension of Lundberg's weighting estimator to the setting of time-varying treatments to estimate black-white earnings gaps under a series of stylized interventions. Specifically, we consider both race-neutral and race-conscious expansions in college attendance and also in bachelor's degree completion. And we found that to substantially reduce the black-white earnings gap, we need interventions that both boost rates of college attendance and bachelor's degree completion, and also close racial disparities in these transitions. So this is a new paper that's is forthcoming in American Sociological Review. It isn't officially out yet, but here you can take a peek at our abstract. So this is a kind of a application of Lundberg's gap closing estimate, but more generalized to a time varying setting where we try to assess the impact of potential interventions at both the college completion and the college attendance stage. So what now? What are we trying to do in this new paper? The goals of this paper are twofold. First, we try to review, explicate, and also contrast the two distinct approaches to studying group disparities, which we term the descriptive approach and the prescriptive approach. So for the descriptive approach, we highlight a generalized KBO, or what we call Duncan decomposition, as you will see why in a moment, that considers multiple sets of explanatory variables sequentially. So this is a technique that is not well appreciated in the previous literature. And for the prescriptive approach, we introduce new interventional estimates that are more akin to real-world policies. And for all estimates, we provide model-free definitions, non-parametric identification results, and the user-friendly estimators. And we finally illustrate the two approaches by applying the analyzing the black-white gap in college completion rates in the US. So far, so good?
Yes, that's great. Thank you.
Yeah. So here is a running example we're going to use, just the black-white gap in college completion. As we mentioned earlier, we know that in the US, Black college goers are much less likely to complete a bachelor's degree than their white peers. A recent study found that among those who started a 4-year college in 2010, 6-year graduation rate was about 64% among whites, but only about 40% among Blacks. And the higher education literature has also identified a couple of contributing factors to racial inequality in completion rates, including racial disparities in economic background, racial disparities in academic preparation, racial disparities in college quality, and also the psychological burden of negative stereotypes that Black students often face in campus life. So keeping this example in mind, let's briefly review the canonical KBO decomposition. Specifically, let's consider how family income contributes to the black-white gap in college completion rates. Here in this setup, we use Y to denote college completion, a binary indicator of whether a student completes college. And we use R to denote race, where 0 denotes maybe white and 1 denotes black. And the explanatory variable here, let's just consider one explanatory variable, family income. Okay. And the goal here is to decompose the gap into two components. A component explained by racial differences in family income, and a component not explained, or residual component. So how does the KBO decomposition work? First, we compute race-specific completion rates, just the sample averages of college completion for Black students and for white students. Then we can fit a linear model of college completion on family income among Black students. And finally, we can see how the model predicts if we substitute white students' family income for Black students. Okay, and here, if we use YB bar predict to denote the average predicted value, then the canonical KBO decomposition can be written as equation 1, where the first component, the difference between the observed completion rates among Black students and the predicted completion rates among Black students if they had white students' family income, according to the model. Okay, and this component is denoted as delta explained, reflects the black-white gap in college completion explained by racial differences in family income. And the second component, denoted as delta unexplained, denotes the residual gap. Okay. And we could also zoom in to see how these components are related to regression coefficients. Here, I used just the alpha B and the beta B to denote the intercept and the slope estimates from a regression of college completion on family income among Black students. And we can similarly use alpha W and the beta W to denote the coefficients from a similar regression among white students. Then the decomposition can be just written in terms of these regression coefficients and the means of these explanatory variables, family income. And you can see the explained component, delta explained, is just the racial difference in family income, XW bar minus XB bar, multiplied by the regression coefficient of family income among Black students. And we could also use beta W hat instead of beta B hat to measure the explained component. Then we have an alternative decomposition where you can see the explained component is again the difference in mean in X multiplied by the coefficients among whites, not among Blacks. Okay. So this is just two versions of the widely used KBO decomposition. And these equations, they use different, you can see they use different reference groups for the explained component. So they have a slightly different interpretations, right? Especially if we wanted to interpret the components in a so-called counterfactual sense. So in equation 2, you can see we can think of it as, you know, how much would the Black completion rate rise if the average family income of Black students rose to that of white students. But if we look at this explained component in equation 3, this counterfactual interpretation would become how much would the white completion rate fall if the average family income of white students fell to that of Black students, right? However, these counterfactual interpretations are not so tenable unless the regression coefficients of family income capture the causal effects of family income on college completion, which is often not the case because we are not addressing the causal effects in this analysis, right? So it's just more prudent to use purely descriptive interpretations for a decomposition analysis. We could interpret these components as reflecting, you know, how much of the black-white gap in completion rates can be statistically explained by racial differences in family income, but not causally explained. Now let's move on to a more non-parametric formulation of the KBO method. We note that the population counterparts of the quantities YB bar, YW bar, and YB bar predict can be written non-parametrically as the mean completion rate among Black students, right? The mean completion rate among white students, and the conditional mean completion rate given family income among Black students, then marginalized over the family income distribution among white students, right? And then the explained and unexplained component can be written as the difference between theta and mu b, and the difference between mu w and theta, right? And if the linear models for the college completion among Blacks and among whites are correctly specified, then the canonical KBO decomposition will target these quantities. However, these quantities are defined non-parametrically. They are not depending on any statistical model, either linear regression or Rorty model. They're defined, in a model-free fashion. Right? So in this sense, the non-parametric decomposition, non-parametric formulation breaks the KBO method free from linear models. And this is a point that cannot be overemphasized. In fact, it echoes the call of a recent ASR paper by Ian Lundberg, Rebecca Johnson, and Brandon Stewart, called this paper, What is Your Estimate? Right? Some people may have seen this paper before. So it echoes the philosophy or the spirit of this paper by precisely defining the estimate of the KBO decomposition without referring to a statistical model, right? Which improves the clarity and the transparency of our research goals and assumptions, and also opens the door to alternative estimation strategies, as you will see. So now let's talk about estimation strategies. Okay. The non-parametric formulation suggests that we only need to estimate three quantities, right? The mean completion rate among Black students, the mean completion rate among white students, and also the counterfactual or the imputed completion rate among Black students, if their family income, follow the distribution of family income among white students. So how to, we can see that the first two quantities, the mean completion rates for the two racial groups, can be estimated directly using their sample analogs, the Y bar and YB bar and YW bar, right? No model is needed to estimate these quantities. Then how to estimate theta? First, we note that theta can be written as a iterated expectation, right? As you can see from the last quantity. We first take a conditional expectation among Black students, then we marginalize over the distribution of X among whites, right? So it can be written as a iterated expectation. And this iterated expectation expression suggests that we can estimate this quantity using a regression imputation approach. So how to implement it? We can first fit an outcome model given family income and also race. Then we can obtain predicted values of college completion when race is set to be Black, right? Then we can average these predicted values just among white students, which is, the outer expectation in equation 4, right? And if this conditional mean function among Blacks is estimated using a linear model among Black students, then the regression imputation estimator will coincide with the estimate in the canonical KBO decomposition, which relies on the linear model specification. But from equation 4, you can see that the outcome model doesn't have to be linear. It could be a loaded model, it could be a probit model, it could be a Poisson model, or even a complex black box machine learning model. Okay, and the estimate is still well defined. And the estimate theta can also be written equivalently as this equation, you can see this equation is very, looks very different from the regression imputation expression, but it's a mathematically equivalent. And this equivalent expression suggests that we can use a weighting estimator to estimate this quantity. And the weighting estimator involves fitting not an outcome model. We don't need an outcome model in this case. We can just fit a so-called propensity score model for race, where we use race as the dependent variable. We use covariates X, here family income, as the independent variable, right? We fit such a model for group membership, and then we obtain the predicted conditional probabilities of being Black or being white given family income, and plugging this estimate into this expression to estimate theta. And we can also combine regression imputation and weighting to form a doubly robust estimator, which will be consistent if either the outcome model or the propensity score model for race, but not necessarily both, is correctly specified. And we'll talk more about the doubly robust strategy later on when we talk about generalized the KBO method. So this is just a canonical KBO method and this non-parametric formulation. We can see once we view things non-parametrically, we decouple the estimand from the linear model, and also the decoupling opens the door to alternative estimation strategies such as weighting and doubly robust estimator. Okay, any questions so far?
Looks like no questions in the chat so far, so please continue.
Okay, sure. Okay, now we're done with the canonical KBO decomposition and this non-parametric formulation. We might ask, what if X, the covariates, are multidimensional, and we would like to assess the contribution of each component? For example, in our decomposition of black-white gap in college completion, the covariates could include not just family income, but also test scores and the college quality, right? So in this case, we might want to tease out their respective contributions to black-white in gap in college completion rates. And in the regression imputation approach, if the model for the conditional mean of the outcome is estimated using just a linear model with no interaction terms, then both the explained component and the unexplained component can be subdivided into covariate specific contributions. And this is often called a detailed decomposition in the KBO literature. However, such a detailed decomposition has a couple of limitations. First, it is not model-free because it depends on the linear specification of the outcome model. Actually, if the outcome model is nonlinear, we don't have a neat detailed decomposition. Also, it suffers from the so-called omitted group problem. Specifically, elements of the unexplained component will depend on the choice of the reference group or the omitted group in the regression model in an arbitrary way. And this problem is especially acute if we have categorical covariates. And finally, the covariate specific contributions can be hard to interpret. This is especially true if these covariates are causally ordered. For example, we can reasonably expect family income to be causally prior to test scores, right? We can imagine family as affecting a children's academic achievement, right? And we can also expect test scores to be causally prior to college quality. Students with higher test scores are more likely to get into selective colleges. So in such cases, it would be more natural to tease out contributions of family income and test scores and college quality progressively or sequentially, rather than in a way that treats them symmetrically as in the detailed decomposition. Because in the detailed decomposition, we just do a kitchen sink model, right? Where we throw all the covariates into the model and see their contributions net of each other. But if the covariates are causally ordered, we might want to tease out their cumulative contributions, one by one. And in fact, the idea of such a cumulative or sequential approach is not new. It even predated Blanda and Oaxaca's influential papers in the 1970s. This is an article by Otis Dudley Duncan, written in 1968. So in this article, the key question Duncan tried to address is whether the persistence of racial economic inequality in the US across generations is due to an inheritance of poverty or inheritance of race. So to address this question, Duncan conducted a sequence of KBO decompositions for the black-white income gap, adding one covariate at a time. Of course, Duncan did not call this KBO decomposition or Blanda-Oaxaca decomposition because it was written actually 5 years earlier than Blanda and Oaxaca. So he added one covariate at a time. First, he fit a model where the right-hand side includes only class origin measured by father's occupation. And then he added number of siblings as an indicator of family structure. Then he added respondent education. Then he added respondent occupation. And for each model, he conducted basically a KBO decomposition. So he teased out the net contribution of each covariate by comparing the explained components of two consecutive models. For example, the difference in the explained component between the first model and the second model reflects the net contribution of racial differences in the number of siblings after racial differences in class origin are accounted for, right? And as far as we know, this is the first paper that used a sequential approach to assess the contributions of different covariates. Although Duncan was very modest, he made no claim of methodological contribution in that paper. That was a substantive paper. He made no methodological claims. So we now try to provide a non-parametric formulation of Duncan's approach, which we might call a generalized Duncan decomposition or a generalized KBO decomposition. Okay. So let's just use x1, x2, all the way to xj, capital J, to denote J-ordered sets of covariates that may contribute to the disparity of interest. Okay. So in our example of the black-white gap in college completion rates, we could consider x1, being family S, x2 being family structure, x3 being indicators of ability and behavior, which could be measured by, test scores, high school GPA, and indicators of substance use delinquency, as you will see in our data set. And x4 denotes contextual factors, peer influence, or school characteristics. And x5 denotes college quality. Okay. And it might be argued that these sets of covariates are temporally or causally ordered, although this is not really required for descriptive interpretations, which we advocate for the KBO decomposition or generalized KBO decomposition. So we use x a bar J, so this is actually a different notation. This is an overline instead of bar. So it doesn't represent the mean of this variable. It represents a set of covariates from x1, x2, all the way to x little case j. Okay, x1, x2, all the way to x little j, where x0 bar is just an empty set because x0, there's no x0, right? So x2 bar will denote x1 and x2. x3 bar will denote x1, x2, and x3, okay, etc. Then we denote the parameter theta j as this iterated expectation, which is just the conditional mean of college completion given x1, x2, all the way to x little j, among Black students, then marginalize over the distribution of these covariates among white students. Right? And we also note that theta 0 is a trivial case. It equals just the average completion rate among Black students. Then the Black-white gap in college completion rates can be decomposed as in equation 6, right? And you can see in this decomposition, we have not just 2 components, we have J plus 1 components. So each of the first J components corresponds to the contribution of one covariate xj, and the last component reflects the amount of residual inequality. So the delta explained xj reflects the amount of disparity that can be statistically explained by racial differences in xj after racial differences in x1, x2, all the way to xj minus 1 are accounted for. So delta explained x2 will reflect the amount of disparity that can be statistically explained by racial differences in family structure after racial differences in family ES is accounted for example. So now let's move on to estimation strategies for this generalized decomposition. Okay. We can see that equation 6 suggests we need only estimate these quantities, mu b, mu w, and the theta j for all the j in the set of 1, 2, all the way to capital J. And as before, the first 2 quantities are just population means of completion rates among Black and white students, right? So they can be directly estimated using their sample analogs. Then how to estimate the theta j parameters? As before, we can use a regression imputation estimator, right? Just the same estimator applied to xj bar, okay, the set of covariates that we consider in this model, right? And if this conditional mean model within this outer expectation is estimated using a linear model among Black students, the regression imputation estimator will coincide with the original decomposition conducted by Duncan. However, we could also use a weighting estimator that doesn't involve fitting an outcome model, where we just fit a model for group membership conditional on covariates xj bar. Right? So you can see the regression imputation weighting approaches are pretty much the same as their counterparts in the one covariate case, except that we now do this iteratively for j different sets of covariates. We add one covariate at a time, right? And we can also combine regression imputation and weighting to form a doubly robust estimator of theta j. And this is shown in equation 7. So this estimator will be doubly robust because it is consistent if either the outcome model or the propensity score model for race, but not necessarily both, is correctly specified. And another advantage of the doubly robust estimator, apart from the double robustness, is that it is particularly suitable to be combined with machine learning estimates of the outcome and propensity score models, in which case the estimator will be root and consistent, asymptotically normal, and also semi-parametric efficient under relatively weak conditions. In other words, even if the outcome and the propensity score models are estimated using machine learning algorithms that are not themselves root and consistent, then under relatively weak conditions, the theta coefficient, our target parameter estimate, can still be root and consistent. So this is a very remarkable property. And this approach is often combined with cross-fitting, which involves the use of different subsamples to fit the nuisance functions, in this case, the propensity score and outcome models, and to estimate the target parameter. So this combination of doubly robust estimator and machine learning and cross-fitting is an instance of what Cherno-Zhukov et al. Call double machine learning, which is a increasingly popular framework or strategy for estimating targets non-parametrically. So now let's just show how illustrate this approach using a data set from a National Longitudinal Study of Youth 1997. Here we use a sample of Black and white students who attended a 4-year college by age 25. And we use R to denote race, and we use Y to denote bachelor's degree completion by age 29. And we have 5 different sets of covariates corresponding to demographic and socioeconomic background, family structure, ability and behavior, contextual factors, and also college selectivity. So college selectivity is just a dummy variable denoting whether the college the student attended is one of the most competitive, highly competitive, or very competitive colleges in Barron's profile of American colleges 2000. So first, let's look at the regression imputation estimates of our results as shown in circles. So here, the different rows show the observed and also adjusted completion rates among Black students. So you can see the top row represents observed college completion rate among Black students, which is about 52%, right? And you can see the observed completion rate among white students, as shown in the last row, is close to 70%, about 69%, right? So there's about an 18 percentage point gap. And the second, third, and the fourth rows show the adjusted college completion rate among Black students when we account for racial differences in family SES, in family SES and the family structure, and in family SES family structure, and also ability and behavior. You can see that these covariates go a long way toward explaining the gap. In fact, after we account for family SES, family structure, and also ability and behavior, racial differences in contextual factors and in college selectivity have very little explanatory power. And the results are largely consistent if we use weighting and doubly robust estimators. But you can see weighting estimates are generally less efficient as reflected in their larger standard errors. And the doubly robust estimators combine weighting and regression imputation. So you can see the point estimates from the doubly robust approach generally lie between those of regression imputation and of weighting. And this chart shows estimated components of the generalized KBO decomposition, which are basically the other side of the same coin. You can see most of the gap is explained by racial differences in family SES and ability and behavior. And the net contribution of college selectivity, as shown in the second last row, is almost a 0. And this result is pretty similar with weighting and doubly robust estimates. So this is just an illustration of a generalized KBO decomposition implemented using different estimation strategies. Now let's move on to what we call the prescriptive approach to disparity analysis. So why do we need this new approach? As mentioned earlier, unless the effects of the covariates are unconfounded, right, estimates from the generalized KBO or Duncan decomposition have no causal interpretations. So what does this mean? This means any policy implications that we tend to draw from such analysis can be misguided. For example, we found that after accounting for other background characteristics, racial differences in college selectivity doesn't contribute to the Black-white gap in completion rates, right? But does this result mean that the gap in completion rates cannot be reduced by equalizing college selectivity across race? So if we have a policy intervention that can equalize college selectivity between Black and white students, will we have 0 impact on the Black-white gap in completion rates? Not necessarily, because the KBO decomposition is not tailored to answer such questions. Okay? So to answer such questions, we need the new approach, which we call the prescriptive approach to disparity analysis. Okay? So in the prescriptive approach, the basic idea is to specify one or more variables as manipulable treatments And then we ask how much disparity would remain or would be reduced under a hypothetical intervention to these treatments. Okay. So for now, let's consider the case of just a binary and point-in-time treatment. And in our example, our treatment is attending a selective college. So here we elevate one of the covariates, X5, right? Previously, X5 is just one of the covariates we consider in the decomposition. Now we elevate that covariate to the status of a manipulable treatment, right? And we treat all the other covariates as potential confounders of the relationship between the treatment and the outcome. Then we use A star and Y star to denote the treatment and outcome variables under an intervention of interest. Then we can define our estimate, the interventional disparity, as the disparity under such a intervention, right? The expectation of Y star among white students and the expectation of Y star among Black students. So what would be their difference? And because Y star here involves potential outcomes under an intervention, we need to invoke some assumptions so that we can identify the causal effects of selective college attendance on degree completion. Specifically, we need 4 assumptions, and I think I'm already into 50 minutes mark. So sorry for running over, but here I'm trying to go over the technical parts more quickly and focus on the big ideas and the empirical illustrations. So here are some identification assumptions we need to identify this target parameter, which we call interventional disparity. Okay. So the identification assumptions are what we call system invariance, consistency, unconfoundedness, and positivity. The last 3 assumptions are standard assumptions we need for assessing causal effects from observational data. Many of you may be familiar with these assumptions. The consistency assumption is also called SUTVA, stable unit treatment value assumption, first introduced by Don Rubin. But in our framework, we need a new assumption called system invariance, which means the potential outcomes are unaffected by the intervention. And this assumption will be violated if there's interference. For example, if we analyze the interventional effect associated with a expansion in selective college attendance, this assumption might be violated if an increasing prevalence of selective college attendance leads to a dilution of resources that each student receives. That could lower the effect of selective college attendance on degree completion. And under these assumptions, we can identify this conditional, expectation of Y star among Blacks and among whites, right, using equation 8 or equation 9. They're equivalent expressions of the same target parameter. And equation 8 suggests a regression imputation estimate. Here, the basic idea is just we fit a model of college completion given race, the covariates, and also the treatment variable. Okay? Then for each unit, we obtain the predicted values under the treatment and under control, and compute a weighted average of these 2 predicted values, where the weights are the probabilities of treatment and the control under the intervention for this particular unit. So under this intervention, what would the probabilities of attending a selective college for this particular unit, given the background characteristics? Okay. And this weighted average serves as the predicted outcome for this unit under the intervention. Then we ask how these predicted outcomes differ between Black and white students, right? And equation 9, here's the typo. Equation 9 suggests a weighting estimator of the same target, where the weight is a ratio of the probability of receiving observed treatment under the intervention to the probability of receiving observed treatment under the status quo. Okay, so here status quo was denoted by just a p hat or p, and the interventional probability is denoted by p star. So this weighting estimator can be seen as a generalization of inverse probability weighting for estimating causal effects in observational studies. Okay. And you might ask whether we could also combine regression and imputation and weighting to form doubly robust estimators. The short answer here is yes, we could. Actually, if we know the interventional distribution a priori, we can combine these two strategies to form a doubly robust estimator, which was discussed in more detail in Lundberg's paper on gap closing estimates. So the doubly robust estimator, as before, would be consistent if either the outcome model or the propensity score model. Here, the propensity score model is for treatment, not for race, for attending a selective college. Is correctly specified, but not necessarily both. Okay. But we rarely know this interventional distribution a priori, and we often consider a stylized intervention where the interventional distribution is a function of observed distribution of race covariates and college selectivity. So in this case, the interventional distribution needs to be estimated from data because the observed distribution also needs to be estimated, right? And in this case, the caveat is here: the doubly robust estimator may no longer be doubly robust or semi-parametrically efficient. So for this reason, we have this doubly robust estimator might be less desirable than the doubly robust estimator we considered earlier for the descriptive approach. Now let's make things more concrete to consider some stylized interventions in our context, right? So far, we have considered a generic intervention, which we just denote by P star, where P star can take any functional form, right? We did not specify the particular form of this interventional probability of attending a selective college for different kinds of students. For Black students, for white students, for students from different backgrounds. Now let's consider some stylized interventions to equalize college selectivity across race. Okay. First, we could consider a stochastic intervention in which the interventional distribution is just a random draw. Okay, we're attending a selective college among Black students. It's just a random draw from the marginal distribution of selective college attendance among white students. For example, if 25% of white students attend a selective college under the status quo, then for each Black student, we basically flip a coin 2 times. If we get 2 heads, then we send that Black students into a selective college. Otherwise, we send them to a non-selective college, right? So it's just a lottery, right? And this intervention was actually first considered in Jackson and Vanderbilt and also considered in Lundberg. They call this marginal equalization because we equalize probabilities of attending selective college marginally, right? So as we mentioned earlier, this marginal distribution, under this intervention, the marginal distribution of selective college attendance was equalized between students from different racial groups. But in this case, attending a selective college essentially becomes a lottery for Black students, right? So we might call this intervention lottery type equalization. But alternatively, we could try to equalize the treatment, right? Selective college attendance without breaking the association between background characteristics and college selectivity. Specifically, we could apply this particular function, equation 10, to proportionally increase the odds of attending a selective college among Black students. For example, if e to the delta here is 1.2, then in this case, everyone's odds of attending a selective college, given their covariate values, will be increased by 20%. Here we can choose a delta such that the prevalence of selective college attendance among Black students is the same as that among white students, right? So we basically, for white students, we do nothing. For Black students, we proportionally increase their odds of treatment. And this particular functional form was first introduced by Edward Kennedy in a JASA paper, although in that paper, he did not use it to study interventional disparities. He considered this in a different context. So under this intervention, we have the same goal. We have marginal equalization. The marginal distribution of selective college attendance will be equalized between Black and white students. But attending a selective college still depends on background characteristics in the same way as they did under the status quo. So we did not change or alter the association between, for example, high school GPA and selective college attendance, which is more realistic and also more akin to real world affirmative action policies. So this is why we call this intervention a affirmative action type equalization. And in this intervention, the overall share of students attending selective colleges will increase because we did nothing for white students, but we increased the odds of treatment for Black students. And this may not be feasible due to the availability of seats in selective colleges because we have limited budgets, right? And also, even if this is feasible, this could lead to a dilution of resources per capita, right? The resources each student will receive may decline as more students attend selective colleges, right? And this could lead to a decline in the effectiveness of attending a selective college on degree completion. And that would constitute a violation of system invariance because the potential outcomes will be different from the potential outcomes under the status quo. So if you did an intervention that changed the system, the system invariance principle is violated. Right? So to add more realism, we could try to equalize selective college attendance without changing its overall prevalence. So to do that, we could, on the one hand, boost the odds for Black students, but on the other hand, decrease the odds for white students so that the prevalence of attending select colleges will be the same for Black students, for white students, and also the same as the baseline prevalence among all students, right? And of course, this means we need to decrease the odds of attending select colleges among white students, which as we know, is highly contested. And the legality of this is being challenged in the Supreme Court. And all these above interventions try to equalize select college attendance marginally, right? Which is pretty progressive and radical. But we could also consider less ambitious interventions that equalize selective college attendance conditional on some metric of merit, such as high school GPA. And in this case, we call it conditional equalization. For example, if we use Z to denote high school GPA, we could specify an intervention where the conditional probability of attending a select college given high school GPA among Black students is the same as the conditional probability of selective college attendance given high school GPA among white students under the status quo, right? So again, for white students, we do nothing. But for Black students, we make this conditional probability the same as that among white students, right? So this intervention achieves racial parity in selective college attendance, not marginally, but conditional on high school GPA. And we could also add more realism to consider conditional equalization without expansion, right? So here we could intervene on treatment assignments for both Black and the white students, such that for both racial groups, the conditional probability of attending a selective college given high school GPA is the same as a weighted average of the baseline observed conditional probabilities of attending a selective college for Black and white students. And here we choose the weight such that the prevalence of treatment in each racial group will be the same, and also the same as the overall prevalence of treatment, under the status quo. So in this case, there's no expansion, right? We just have a redistribution, but no expansion. And so you can see this intervention achieves racial parity conditionally, conditional on high school GPA, but also keeps the prevalence of selective college attendance unchanged. So these are just some stylized interventions that we consider the The first intervention, marginal lottery type equalization, was considered in Jackson and Vanderbilt and Lundberg. So this is just we introduced this to to review some previous proposals, but the next couple interventions are not considered in previous literature, but we consider are more akin to real world policies. So now we can take a look at empirical results to see how the racial gap in college completion could be reduced, or to what extent it can be reduced under different types of equalizations, right? So here, the horizontal axis shows the amount of gap being reduced under different types of interventions. You can see all 5 interventions can significantly reduce the black-white in completion rates. This result is in contrast to our earlier decomposition analysis, where we saw that the contribution of college selectivity is almost 0 after we account for other characteristics, right? But from an interventional analysis, we can see interventions at this stage can still help reduce the gap, right? The strongest reduction would occur on the lottery type equalization, in which case the gap can be reduced by about 3 percentage points. And affirmative action type equalization with or without expansion could reduce the gap by about 2 to 3 percentage points. And conditional equalization, they are more modest, so they have weaker effects. And the weighting estimates are similar in magnitude, but they have much larger standard errors. So here, the large standard errors are partly due to extreme weights. So from these results, you can see weighting estimates are not so desirable, compared with regression imputation. And we haven't got a chance to implement W-robust estimates partly because the W-robust estimates don't have the theoretical properties that we would expect from W-robust estimates in other settings. So here we could still try to derive semi-parametric efficient estimators, but those estimators will be intervention specific, so there will be no generic formula for semi-parametric efficient estimators. So for now, we have implemented only the regression and imputation weighting estimates, but they give qualitatively similar results. And this chart shows the predicted completion rates for Black and white students under these interventions. You can see the gap is still pretty large, under different intervention. Reductions of the gap are quite small, in relative terms, because observed gap is about 18, 17 percentage points. So a 3 percentage point reduction is only about 15%, right? And reductions are mainly driven by increases in completion rates among Black students, then by declines in completion rates among white students. And this is true even for seemingly zero-sum interventions like affirmative action type equalization without expansion, right? You can see completion rates slightly reduced for white students, but increased to a large extent for Black students. And this is also true for conditional equalization without expansion, although to a lesser extent. Okay, to sum up, we have reviewed and contrasted these 2 distinct approaches to disparity analysis. The descriptive approach is epitomized by the KBO decomposition and its variance. In this approach, all estimands are a function of observed data, not counterfactual data. So this is why we call the approach descriptive, right? It's a useful tool for summarizing our data, just like a scatter plot, to see how data look like. But it might also provide indications of possible causal mechanisms to be explored in more detail. But in itself, it isn't tailored to answer causal questions or policy relevant questions. By contrast, the prescriptive approach interrogates how much of the gap can be closed by various interventions. Right? So it can lead to more rigorous discussions of policy implications. Right? In writing empirical papers, we're often asked to, provide 1 or 2 paragraphs toward the end, telling the reader what the policy implications of your analysis are. Right? And oftentimes those discussions are kind of ad hoc, right? Because the linkage between our analysis and the real world policy can be quite tenuous. But the prescriptive approach is one step toward this direction. It can allow us to have more rigorous analysis of policy interventions. Right? And for both approaches, we can define and identify S-demand non-parametrically. And this last point, is not just for disparity analysis, but hopefully for all social science research going forward, because as Lundberg et al. have convincingly argued, this non-parametric definition and identification of targets can significantly improve the clarity and the transparency of research goals and assumptions. And in addition, it can open the door to a range of flexible estimation strategies, as we have seen for both the descriptive and the prescriptive approaches of disparity. We can use alternative estimation strategies and compare our results. So that's all for this talk. Sorry for running over. This is my first time giving this talk, and there are a lot of loose ends. So I look forward to your criticisms, suggestions, and questions.
Thank you so much, Dr. Joe. It was, even though it's a little bit longer, it's so very useful. I mean, a whole lot of literature that you went through and summarized, and also these new methods that you detailed. I mean, all of it's a lot of it is new to me, and I'm sure to many of my colleagues. So it's really, really valuable what what you've presented today. So I do want to, we do have a little bit of time for questions. So I want to open up to my colleagues. If they have any questions, please do. You can raise your hand, you can jump in straight away, you can write in the chat box. Please don't feel shy. Okay. While my colleagues are waiting, perhaps if I could jump in there with a question. I mean, apologies if this is not a great question, but I was struck by the lower efficiency of the weighting approaches, and it's something the way how you described. So when you're fitting the propensity score model, you're estimating the outcome variable is whether you're black or white. You're estimating model of blackness versus whiteness, and so I'm wondering to what extent the covariates that you're looking at are not really super predictive of being black or white. And so, for instance, if we're interested in really estimating whether somebody is black or white, we might be interested in measuring skin color, for example, as a prediction of that. So we get a really strong model, that explanatory model, and though the skin color variable might just overwhelm any of the other predictors of being black and white. And so that might improve the efficiency of the weighting model, but I didn't, in my head, I didn't quite work out whether that was useful. Whether that would help in any sort of causal interpretation. So those are my vague misgivings, but ideas that came to my head as you were talking about this. What if we improve the explanatory power of the propensity score models that you're fitting?
Thank you very much, Terani. This is a great question. Let me respond in a couple of ways. First, unfortunately, I don't think we have skin color as a covariate in this data set, so we don't have skin color here. I think, kind of more important point here is, first of all, the inefficiency of weighting estimators is well known in the community, and people recognize this problem. So they have different strategies to kind of address the problem of unstable weights or extreme weights. So there's a tension here between predictive accuracy and also efficiency of our estimates of the target parameter, because weighting is based on propensity score models. But we are not really interested in estimating those models per se. We are using those models as nuisance functions to construct our estimates of the target parameter, right? So we have two targets. Our true target is the target parameter, like the decomposition, like a causal effect estimation. But the propensity score model itself is not our target. So if we try to come up with the best propensity score model ever, if we try to improve the predictive accuracy, we can go on adding more and more covariates forever. That will increase predictive accuracy. But on the other hand, as we increase predictive accuracy, the propensity scores can be very close to 0 or 1, right? So when the propensity scores are very close to 0 or 1, they go into the denominator of our weights, right? So when the propensity score is really close to 1, when the propensity score is really close to 0, right? Then the weights can blow up, right? So it can be very unstable to cases where you have propensity scores that are close to 0 or close to 1. When propensity score is close to 1, though, because the weight sometimes the denominator is 1 minus the propensity score, so the denominator can still be arbitrarily close to 0. So in those cases, the weights can be very large, not because the true weights are large, but because of the unstable in our propensity score estimate, instability in the propensity score estimation. So this is a notoriously difficult problem in all kinds of weighting estimators. So in this example, I followed a suggestion by Hernan and Robbins in a 2008 paper. I trimmed the weights at the first percentile and the 99th percentile. So I just censor the weights, censor the extreme weights, but we're still, I censor not just the very large weights, but also censor very low weights in the hope that we don't shift the distribution to the right or to the left. So that's the one thing I did in this analysis. But you can see even after we trim the weights, which is not so desirable for unbiasedness concerns, but we still have more more inefficient estimates from the weighting approach than from the regression imputation approach. So here in the decomposition, in the descriptive approach, the generalized KBO decomposition, we can see that the regression imputation estimates are based only on the outcome model, right? The propensity score estimate, the weighting estimate are based only on the propensity score model. So they are not really, we don't have strong reasons to prefer one over the other, right? Because the outcome model could be misspecified, the propensity score model could be misspecified. But in this case, we have a stronger case to prefer the doubly robust estimator because it is consistent if either model is correctly specified. So it's more robust in this sense and more credible. And you can also see the doubly robust estimator is generally more efficient than the weighting estimates, although they're generally less efficient than the regression imputation estimate. So in terms of efficiency, the doubly robust approach lies in between. But in terms of robustness, it comes up on top. So if you ask me to rank the desirability of different estimators for at least for the decomposition, KBO decomposition, I would prefer regression imputation and doubly robust over weighting estimates per se.
Great, thank you so much for explaining that so clearly. Thank you. Are there any? Oh yes, Dodo, please go ahead.
Hi, I just want to pop up and say hi. Long time no see.
Hi, yeah, long time no see.
Yeah, thank you for giving us such a wonderful presentation. Although I'm not sure I can understand all the technical details, but I think your method is really innovative and bears important policy implications. Because before, when we are reluctant to use causal languages when we use KBO method, because the social grouping variables we care about, like gender, race, are really not immutable. We cannot like manipulate one's gender or race like we manipulate other treatment conditions. But your method helps us to identify certain social processes that the policy can intervene and help to reduce inequality, which is so great. So I only have two small questions. One is, so for both of these approaches, I see that you're apply them to two group comparison contexts, like black, white, or male, female. Is it possible to extend the method to multiple group comparison contexts? And the other question is, I wonder whether you have tried to apply your method to the Chinese data set like CFPS, and if yes, what are your new discoveries or policy suggestions? Thank you.
Thank you, Dodo. These are great questions. Yeah, for your first question of multi-group comparison, I think the short answer would be yes. Actually, we do plan to incorporate not just the Black and white students in the empirical demonstration, but also Hispanic students in our analysis. We still need to define our target. So if you take a look at our illustration, our target parameter is just the interventional disparity between two groups, right? The counterfactual completion rate among whites minus the counterfactual completion rates among blacks. When we do analysis of multiple groups, we could still do, for example, pairwise comparisons, right? So the disparity between whites and Hispanics or whites and Asians, right? So we could have multiple target parameters. That's totally fine. But I don't think there's a convenient one number summary to capture disparities across multiple groups. We still need to do more fine-grained pairwise comparisons to have a full picture, right? So that's totally fine. We just need to consider different pairs, right? And yeah, Chinese data sets, of course, the more the better, right? So we so far, I think I've been practicing this approach, in one of my more recent papers on U.S. earnings gap between Black and white Americans, and yeah, so I don't think so for the two approaches, I think the descriptive approach epitomized by the KBO decomposition, this approach doesn't really have stringent requirements on our data, right? Because we're not trying to identify causal effects, and we don't need any identification assumptions. As I mentioned, KBO decomposition per se is just a data summary device, but it's really useful for us to see the associations and see how different covariates statistically explain disparities or gaps, right? And so yeah, I don't think we have data requirements for the KBO decomposition, even the non-parametric version. As long as we have a large enough data set, we can get pretty precise estimates of different explained, unexplained components. And I think it's more suitable for data sets where we have a large N and large P, right? When we have a large data set with a lot of covariates, the parametric models will be less and less credible, right? And so, the W robust approach, as mentioned, can be combined with machine learning estimates of both the outcome model and the propensity score model for group membership. And the weak conditions I briefly mentioned are that as long as those models converge the truth at a rate of n to the negative 1/4, which is a much slower rate than root n, we can still have root n consistent estimates of our target parameters, which are the unexplained components. So I think this is really a promising direction, for future scholars of to do decomposition analysis. You can totally forget about the linear model-based framework and subscribe to the non-parametric version, which opens the door to much more flexible and robust estimation strategies. And for the interventional approach, for the prescriptive approach to study the impact of different interventions, we do need to have credible assumptions on confounding, right? Especially the unconfoundingness assumption, right? So if we are confident we have collected a large set of covariates to remove most of the confounding between the treatment variable and the outcome, then we are ready for a interventional analysis, for analysis of interventional disparities, right? So the key assumption here is unconfoundingness. Whenever we are ready to assess the causal effect of some treatment, where we can use the same data set to look at interventional disparities.
Okay, I'm not sure if we have many more questions. I'll just keep talking in case there are one or two, any extra questions. I also wanted to thank you, Dr. Zhou, so much for the paying homage, making sure we remember Evelyn Kitagawa and the story about how her contribution was ignored by the economists. It's quite remarkable, especially when we're talking about discrimination in labor market outcomes. So
yeah, exactly. If you look at Blanda and Ohaka's original papers in 1973, both papers use the example of gender discrimination, and they didn't cite Kitagawa. So it's very ironic. And I also think Duncan's contribution was underappreciated. Although I did notice Blanda or Ohaka cited Duncan, but they didn't make a big deal of that. Actually, I think both Duncan's decomposition and Kitagawa's decomposition are more general than the decomposition done by Blanda and Ohaka, because Duncan's is more generalized version of the linear model-based decomposition. And the Kitagawa's, actually, if you look at Kitagawa's paper, it's entirely non-parametric, right? So the Kitagawa's formulation of this decomposition is based on a non-parametric setup. So it didn't really rely on parametric linear models. So in that sense, it's also more general than the Blanda-Ohaka approach.
That's great. Any other questions from colleagues?
Tarani.
Yes.
Yes. Paul. Yes. Thank you for a very interesting talk. We really like to hope to train our graduate student. To be able to understand. I think the talk. The talk itself is there's a lot of substance there, and thank you very much for the job. May I just have one question about the assumption about the unconfoundedness, right? I think you assume some orthogonality between the Y and A. Is there any testing testing the validity of this assumption? I think in practice, I think to be able to check that that assumption are valid before I think we have a full appreciation of the result.
Yeah, thank you. This is a great question. So the unconfounding assumptions itself is not testable or verifiable, but we could, in practice, I think researchers can do two things. some people have proposed the so-called placebo test to see if the treatment has a impact on something that is not expected to be affected by the treatment. So some placebo tests can, if the data fail the placebo test, it casts more doubt on unconfoundedness assumption. That's one thing researchers could do. And another thing that is more routinely done in empirical research is just to do a sensitivity analysis to see how the result is changed under a hypothetical confounder of the treatment outcome relationship. So yeah, so those are the things we could do to add more robustness to our results. But the unconfounded assumption per se, I don't think there's a test for it.
Thank you.
Because it's an independence between observed variable and a unobserved variable, right? The one of the two variables unobserved. So that's why we can't really test the independence.
So it's going to be the hour now. So I'd just like to thank our speaker today, Dr. Xiang Zhou, for such an excellent presentation. It's he's introduced me, I'm sure to all of you, a range of new literature and new methods that are really important for developments in the social sciences. So a big thank you from myself and my colleagues. Thank you so much for your presentation.
Thank you very much, Dhirani.
Okay.
It's a great pleasure to share my work. It's still rough. We don't have a manuscript yet, so but I hope I can gradually develop the paper as I talk more and more about it.
I look forward to reading about it.
Hi, Xiang. Just wanted to say hi. I'm really inspired by your talk, and I need to talk to you more because we're actually, Dodo and I are working together on some new project, and maybe we could use your approach. And I wanted to ask some questions. I don't want to spend more time today because it's already pretty long, but we are probably interested in non-dichotomous those kind of predictors, not just the black and white, but by some continuous variable. And of course, we can always dichotomize a variable.
That's a great question. Actually, we do plan to to generalize to continuous background category to not consider categorical inequality, but also inequality across like SES, a continuous dimension.
Right.
That's one thing we'll explore.
Wonderful.
Another thing we'll do generalize this approach to settings where we have a continuous treatment, right? Not just whether a college is selective or non-selective,
Yes.
but also continuous treatment variables. So those are two directions that we'll definitely go after.
Okay, wonderful. I'll send a message to you about this new set of ideas today, actually.
Thank you.
Okay, thank you. Bye.
Thank you very much.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.